Welcome back to Math 135. We are on lesson 27. We're going to continue looking at exponential growth and decay. It can go either way, whether it's increasing or whether it's decreasing. And one of the things that I like today is that we can kind of look at an exponential model that may be a better predictor for population growth than our basic uninhibited growth model. Okay? So to get started, we're going to jump right into that really cool guy. And I know there's a lot of writing there, but I wanted you to know this source. I decided it would be awesome to work with data. Because, you know, really one of the most useful ways for math and functions to be used by many people in science is that after they get their data, they try to get an equation to fit that data. So it says first fitting to real biological data was done by Tor Carlson, and I'm not even going to try to pronounce the name of his paper, but he's counting, let's see here, what is he counting? Yeast, a certain kind of yeast. The biology people can check that out for me. And I did get you a picture of what might be yeast. But Tor's looking at something like this under his microscope, and he's counting. And he makes this table of data that at time 0 he has a population of 9.6. Not sure how Tor got that, but this is his data, so we're going to work with Tor's data. Okay? So what I'd like you to do, if you have pulled down your handout from Blackboard or some other, from your Missouri State Connection, grab a hold of that graph and your data, and I'd like you to plot the points. Now, I've already made these increments. We're going up by 25s on the y-axis. Okay? So at time 0, we're down about here. Oops, that went a little low. 1 is at about 18. 2 is at about 29. Now take a few minutes and plot that. In fact, you might want to pause me so that you can get those all plotted. I already put the graph in. I put the data into WinPlot. Remember, WinPlot is one of our options. And look at that graph. That is just some amazing data. And if you think about population growth, you know, a lot of times we've had this exponential model that does this. And it just keeps going forever. And do you really think that a population is going to keep increasing, that uninhibited growth, forever? I'm not a biology person, but I really think there are enough constraints around that are going to control that population. And so actually, this data seems to be a very sensible approach to populations. And then what I did is finagled around between a graphing calculator giving me a model and playing around with it. And I came up with this particular equation, not a pretty sight, but 663 divided by 1 plus 74e to the negative 0.55t. Wow. And I asked WinPlot to plot that curve, and look at how nice that is. Now, in all honesty, the scale was very generous to me as far as how well I really hit those points. But you know, for trying to come up with an equation to fit data, that's not a terrible result in my mind. Now, when does it appear, based upon your graph here, when does it appear that the population might be growing the fastest? Well, you know, in the beginning, you don't have that many bacteria to be procreating, however bacteria do that. But at some point in time, the growth of the population kind of picks up. But then those constraints start to affect it and start to slow down the growth on that population. I said, does it appear that there's a maximum population? You know, I've had some students in class say, it kind of looks like there might be a horizontal asymptote up there at the top. One down here as well. You know, sounds like a great idea to me. Okay? If so, why might that be the case for a given population? Well, it could be that at some point in time you've kind of maxed out how much population a particular environment can sustain. Now, of course, you need to talk to the biology people for a better understanding of all that, but I think this is a reasonable, basic observation. Now, I would like for you to use that equation that I gave you and find out what the population would be in 30 hours. Because you'll notice that TOR's data only takes us up through hour 18. So what I'd like to do is kind of see what's happening to this curve as we go past that point in time. Okay? Well, I'm not doing this in my head, so I went ahead and put in the 30, makes that exponent, because here's where you multiply the time times that constant value. Wow, look at that decimal. Now, I put this all in here because I wanted you to see, if I take 74 times all of this, you realize it's still going to have a lot of zeros. So when I add it to 1, do you realize it's about 1? And you know, it's kind of fun when I have the students do this in class because I'll just tell them, okay, put 30 in your calculator and tell me what you get. And they run all those calculations. Hey, do be careful. As you enter this into your calculator, you're going to want to have 663 divided by and open up parentheses for that entire denominator. Because you might be looking at some different answer and wondering why. Put 1 plus 74 times E. Now, depending on your calculator, it may open up a parenthesis for you when you select that E, negative 16.5, close and close. So make sure you enter it all in that particular way. And students will do that and they get the answer of 663 and they're like, well, that's kind of odd. But no, it really isn't. And then, what if we go out to 100? And I think his units were hours? 100 hours? Well, look at what my calculator tells me is E raised to the negative 55 power. It's 1.3 times 10 to the negative 24. You realize that's daggum close to 0. And so that denominator is essentially extremely close to 1. So what does this illustrate? Well, it illustrates that I've got that horizontal asymptote going on there because I'm going to get ever closer to that 663 because what's going to happen is this denominator is never 1, but it's going to be getting extremely close to 1 as this part gets even closer to 0. Okay, well then apparently 663 must be something kind of important. It's what we call the carrying capacity for that particular environment, meaning that that's like the most that it will take. And in fact, this is called logistic growth. And that was the other model that I mentioned in the last lesson. We have 2 models for exponential growth. This guy, which is called logistic growth, and this uninhibited growth model that you've been seeing now in several lessons. Okay? Well, in this particular case, when you're using the logistic growth model, then the carrying capacity is going to be n. Now you might say, why? Why does that happen? Well, as t gets to be really large, And by the way, we found it didn't have to get real large, did it? As t gets large, we have e raised to this negative number. Well, remember what negative is going to indicate. It's going to be 1 over e to this large exponent. Well, that's going to get very close to 0, and so adding it to 1, essentially that denominator is heading towards 1. Okay? So, n, this number in your in your numerator, is going to be your carrying capacity, which is essentially the maximum population that environment should be holding, according to this model. Okay? Now, what I'd like to do, anytime you use a model, a mathematical model for a problem, you want to have a sense of, well, how good was this model? So what I've done, and I apologize, this stuff is awfully small and it's kind of all scrunched here together, but you guys can lay out your handouts. Here's my graph where I had my data plotted and I put the equation, and that equation is the model, the mathematical model. And here's the graph going along with that. Now here's Tor's actual data. So this is what really happened, okay? Then what I want us to do is use this equation, this 663. Remember, I kind of created that from running a regression equation on my TI graphing calculator, but then I also adjusted it to get it into the form that I wanted. So this is kind of a finagled equation. Put t equals 1 into here, and I get 15.7. Now, if you look at 1, Tor's data says 18.3. Well, we're not far off. We're not exact, but we're kind of close. When t equals 6, and you plug that in, you get 177.8. Well, at times 6, he has 174.6. And by the way, it's also kind of interesting from the graph. If you've got the big graph from before, you can see that that curve is just slightly above the data point there. Okay, and yes, my model gave me a value a little bit higher than his data. When t is 12, we get a 602. Not too bad. And when t is 18, my equation says 661, Tor says 661.8. I'm okay with that. Now, by the way, according to my model, what is the carrying capacity for this environment? Remember where you find your carrying capacity? When it is in this form with 1 plus a constant times e, this numerator is your carrying capacity. So that carrying capacity is 663. Okay? It's a kind of handy model. Well, then I decided to change and see if I could come up with another sample. So I stole one from a Ron Larson textbook. Thanks, Dr. Larson. An intermediate algebra text. And using billions as your unit, based upon the U.S. Census Bureau data, using t as the number of years since 1990, this would model the population of the world. Okay? Well, let's use that model to find the population in 2020. Now, if you're going to use this model to find the population in 2020, what are you going to do? Well, you'll notice that essentially everything's in there except the t, and the t is number of years since 1990. So you're going to put, let's see here, to get to 2020, what, 30 years? 30 years. And when you run those calculations, we get 7.6 billion people. Should be around in 2020. Now I was thinking, man, that's a lot of people. And I can't tell you right now, it seems to me we've passed 6 billion. I don't know if we've gone past 7 billion yet as a world population. But I thought, you know, I wonder how close we're getting to our carrying capacity. All right? I think that's an interesting question. So what is our carrying capacity? It would be 11.7. Okay? So the question is, what percent of the predicted maximum population? That's the same thing as carrying capacity. And so I would compare the 7.6 to the 11.7, 65%. I think that's kind of interesting. Of course, you might play with that model some more. You might see what it predicts for 2010 and see if you can come up with that number and see how good this serves as a model for the data, which of course is something that the scientists always care about when you're using a model. Does it really have any value for me? Okay, well, now that we've had a chance to see the logistic growth, I thought I might go back and review with you kind of the uninhibited growth model. So, in 2000, we had about 109,500,000 cell phone users just in the US. And then by 2006, it's up to almost 233 million. And I said, let's write a function to represent this. Now, I switched it over to the uninhibited growth model. And I'll tell you, I'm being totally honest, why? Because it's too hard to work with the logistic model as far as coming up with those. That takes a little bit of time and effort. So we'll do a little bit simpler one, and we'll look at it as uninhibited growth. Now, if it's uninhibited growth, that means we're talking about this guy right here. A equals A naught e to the RT. And so what you have to do is see how you can fit that information in. Now this is really similar to the problem that I did in the previous lesson. That's why I said it's review. It's a lot like that population of Texas problem. Remember that guy? Yeah. See, what I can do is decide to use the earlier time that I know some information about, this 2000, let's use that as our beginning, our 0 time, okay? So the amount in 2000 is, I'm going to say 109.5. Now, as soon as I do that, do you realize that means my amount is always going to be in millions? I just don't want to write all those zeros. So 109.5 e raised to some constant, and I don't care if you use a k or an r, then the time. Well, the next date that I know something about is 2006. So I'm going to say k times 6, and that has to equal then 233. Now take a second and digest this. Are you okay with what happened here? Because we've solved this kind of equation before, and I've got it kind of worked out here if I remember. So here's my basic equation. And of course, to bring this 6k down, I need to use logs. And why did I use ln? Because there was an e in the problem. Made it the easiest thing to do. Okay, and then my k value is 0.126. You see, what's very interesting about this model is if you've got the right information, you can compute that constant. Remember I told you that constant is inherent to each problem. Okay, so don't assume that if you know the constant in one problem that you can just import that to another problem. No. But for this particular one, it means then that my equation is going to be that the number of cell phone users in millions is going to be 109.5 e to that exponent. And notice that I have to tell you, just like that textbook always does, that N is going to be in millions, although I didn't type it. And T is the number of years since 2000. Because you see, that's what I used in order to write the equation. So then I just have to pass that information along to you. Okay? And we end up with, for 2009, I decided to check to see, all right, how many should we have had in 2009? That means my t value is going to be 9, and I come up with about 340. Now, of course, that 340 is what? It's 340 million users. Well, then I thought, hey, why don't we check and see if that's at all accurate? Well, I had a little trouble finding it, but according to Wikipedia, they actually had how many cell phone users in the U.S. in 2009? It said 277 million. So then you say, well, how good was my model? Maybe uninhibited growth wasn't the best way to do that. Okay? You know, maybe the market kind of got saturated. And you know, if you think about it, the idea of marketing anything is kind of the same idea in that in the beginning there's going to be very few, but then as people find out, oh, this is a great product, and you might have some great marketing strategies, it takes off and you have major growth, and then you've kind of saturated that market and it's going to level off. So hey, maybe the logistic model would have been a better model for this. So let's go ahead and recap, and this is our second look at some exponential growth. We've got two basic kinds of exponential growth and decay that we've looked at, and there are some others. But if you are in a situation of uninhibited growth or decay, you're going to use this particular guy. Hey, do you remember when we first saw this equation? When was the first time we used something like this? Well, you might recall that it looked like this. Do you realize that's the same thing? What was the P? The P was principal, and principal is the beginning amount of money, and this was for continuously compounded interest. Remember all that? Okay, well that's the exact same thing. If your money is continuously, uninhibitedly growing, you use that formula, which is this particular one as well. But then for lots of population growth or decay situations, a logistic model may be more accurate. And this is the form that your logistic growth is going to come in. And we probably could have written an equation. The carrying capacity of the environment is then N. Okay? Well, do some practicing with those, and I really hope that you'll connect it back to everything else we did. I also hope that you're starting to feel much more comfortable with just pulling out those logs and using them whenever you need to solve an equation where your variable's sitting up in that exponent. Okay? So we've kind of finished all of our tough work here with exponential and logarithmic functions, and I hope you're feeling really good about it. And I'll see you later.